Hi there, physics fans. In the last episode, I told you about astronomical mysteries that have led some scientists to postulate that there exists an unseen form of matter that is 5 times more prevalent than all of the stars and galaxies seen by the best telescopes. Seeing the unseen sounds like a perfect topic for this week's episode of Subatomic Stories. From the 1930s, astronomers saw galaxies both spun and move through space more quickly than expected. They saw images of distant galaxies more distorted than they could explain. Truth be told, it's a bit of a mess. Even today, we still don't definitively know the explanation. The most accepted answer is that a substance exists called dark matter. But first, let me kind of breeze through ideas that were investigated and discarded. In the last video, I mentioned a delightful analogy that I believe originated with Stacy McGaugh, professor at Case Western Reserve University. He treated the observed discrepancy as roots of a tree whose branches and leaves are a metaphor for potential solutions. If the issue is a disagreement between the motion of stars and galaxies and their observed gravity, then it stands to reason that scientists either misunderstand how astronomical objects move or the gravity that governs them. Ideas on how researchers may not understand motion fall under the umbrella name MOND, short for Modified Newtonian Dynamics. The first MOND theory was proposed in the early 1980s, and it did a brilliant job explaining away the discrepancy of having the outer edge of galaxies rotating too fast. The original theory didn't do as good a job on the other mysteries, and the theory was obviously incompatible with the theory of relativity. In recent years, scientists have devised improved versions of MOND, which do a better job and are now relativistic, but there are 2 observations that make me personally lean away from the MOND explanation for the mysteries at the root of the tree. I'll get to those in a moment. If the answer isn't misunderstanding motion, then what remains is gravity. Gravity could be wrong because we literally don't understand the theory of gravity or because there is invisible matter. That's the next branch in the tree. Both of them remain possible explanations. If the issue is unobserved matter, then we can ask what kind of matter it is. In the 1980s, the most obvious and least adventurous explanation was that perhaps there were invisible astronomical bodies like black holes, brown dwarfs, and planets that have been ejected from their solar system and now wander the stars. Researchers looked for these objects called massive compact halo objects, or MACHOs. Some were observed, but it became clear that there simply aren't enough to solve the mystery. So, scientists turned their attention to a form of dark matter that is essentially a gas throughout space. One thought was that the gas was quick-moving neutrinos, while another thought was that maybe it was a new form of stable, slow-moving, and electrically neutral matter, something like neutrons floating around. When the universe was young, whether dark matter was fast or slow would have strong consequences on how galaxies formed, and we can use powerful telescopes to look at ancient galaxies, and we are quite confident that dark matter doesn't move quickly. Because in a gas, temperature and the speed of molecules are related, we call this form of dark matter cold dark matter. A decade or so ago, physicists thought that the theory of supersymmetry would provide for a cold dark matter particle called a WIMP, short for weakly interacting massive particle, but the theoretical enthusiasm for that has waned of late. WIMPs would be like stable neutrons with a mass in the range of hundreds or 1,000 times that of a neutron. However, if we're being honest now, we really have no idea the mass of individual dark matter particles. They could be far lighter than an electron and as heavy as an asteroid. In fact, we've looked for cold dark matter at all of these sizes and masses and have found precisely 0. Nothing, not a bupkis. And when I say we've looked, I mean we've looked. I could spend hours telling you all of the ways, but nothing. So we're at a point where cold dark matter and modified gravity are possibilities. Is there any reason to pick one over the other? Maybe. Actually, there are 2. The first is called the bullet cluster. This is an astronomical phenomenon where 2 clusters of galaxies pass through one another. If dark matter is real, then a cluster of galaxies consists of galaxies, hydrogen gas, and dark matter. When they pass through one another, the galaxies miss and pass through, and the hydrogen gas collides and heats up in the middle. If dark matter is real, then it should stay with the galaxies, and if dark matter isn't real, then it should stay with the gas. and the data says it stays with the galaxies. So that's respectable evidence that dark matter is real. Now, there are some people who do not find this to be persuasive, so let me tell you about another observation. Most galaxies rotate more quickly than can be explained by the stars and gas they contain, but there are a couple of instances of galaxies that rotate exactly the speed you'd expect solely from the observed stars. If the explanation for Magaw's roots are either modified gravity or motion, it's hard to imagine that it somehow would be turned off in a galaxy. However, it's not too hard to imagine a galaxy that, by chance, simply doesn't contain dark matter. Thus, in a moment of astronomical irony, galaxies without dark matter seem to be excellent evidence for the existence of dark matter. Now, like I said, most astronomers believe that dark matter exists, but it has never been directly observed, and until it does, we have to be cautious. If you're a young person interested in physics, it's an important, unsolved problem, and the person who solves it will be a scientific hero. Okay, let's see what sort of questions we have this week. There were tons of interesting questions this week. Let's jump into them. Balaz Adarjani asks if dark matter could form a black hole. Hi, Balaz. The answer to your question is both yes and no. Assuming dark matter is the particle form currently favored by astronomers today, dark matter exerts gravity just like ordinary matter. If you were to clump enough of it together in a small location, the result would be a completely ordinary black hole. That's the yes part. But that clump together thing is key. Since dark matter isn't affected by electromagnetism, it doesn't clump together. And even if dark matter experiences forces that only affect dark matter, we already have proved that dark matter isn't in the form of massive and compact objects. So, since dark matter doesn't make objects like dark matter stars, we can be confident that dark matter doesn't make dark matter black holes. Good question. Jerry Galweski asks if dark matter could be ordinary matter in some sort of parallel universe. Hi, Jerry. The answer to your question is no, mostly at least. First, ordinary matter clumps into compact objects like stars or galaxies. Dark matter is much more diffuse than that, so even if there are ghost universes, we know that they're not ones in which matter acts like matter in our universe. But there's a much trickier thing to think about. Gravity weakens as 1 over the distance squared. This is a direct consequence of there being 3 dimensions of space. In your scenario, gravity exists in both our universe and the parallel one. That probably means that there are 6 dimensions, which means that gravity should weaken as the 5th power of the distance. Now, obviously, such statements depend critically on the exact multiverse model you're considering and how dimensions work and all that. But hopefully you see that your supposition would require some disciplined effort to carefully lay out a well-developed theory. Vivek Yadav asks if the laws of physics can change over time and if dark matter might convert into ordinary matter. Hi, Vivek. We're pretty sure it can, and this isn't supposition, it's data. For instance, we can look at galaxies in deep space. Light from those galaxies took millions, billions, or as much as 14 billion years to get here. The laws of physics always seem to be the same throughout the history of the universe, so we can rule out your conjecture with some certainty. Ben Ang points to my favorite tree metaphor and asks if dark matter can be multiple leaves on the tree. Hi, Ben Ang. You make a good point. Cosmic neutrinos are a form of dark matter, as are black holes, brown dwarfs, etc. However, we now know enough to know that neither of those things can make up the majority of dark matter. Dark matter is 5 times more prevalent than ordinary matter, and neither neutrinos nor black holes are anywhere near enough. After decades of work, the favorite explanation is that dark matter is likely to be a single form of undiscovered matter. On the other hand, until we've solved the dark matter puzzle, we need to not be closed-minded and focus on a single answer. It remains possible that dark matter is multiple leaves on the tree. However, we can definitively say that we've ruled out many of the leaves as being the main solution to the dark matter mystery. Dam notes that dark matter doesn't interact with light and asks if we could run into dark matter in outer space. Hi, Dam. I think the answer is no. After all, when we touch something, what is going on is an electromagnetic reaction between atoms. Dark matter doesn't experience electromagnetic reactions, so it's likely it would pass through you, just like neutrinos do. Good question. Giovanni P. notes that Mercury orbits the Sun faster than the outer planets and is asking how this applies to galactic motion. Hi, Giovanni. What you said is true, but there is a key difference. Planets orbit the Sun, which is a concentrated form of mass. Stars orbit galaxies, which are a distributed form of mass, and, just as important, stars are actually inside the galaxy itself. The orbit of stars inside the galaxy are governed only by the mass of other stars inside their orbit. The ones outside don't matter. It's easy to show this by inventing an imaginary galaxy that is a solid sphere. According to Newton, the orbital velocity of a star inside the sphere increases as a function of distance from the center and drops off outside the sphere. You can see what I mean here. And I put a link to a paper in the description that shows the relevant math. In the case of real galaxies, the drop-off in orbital velocity at large radii is because the star is outside the galaxy and the mass of the entire galaxy is governing the star's motion. That's like when planets orbit the Sun. Good question. ArtCamp7 asks if the phenomena of light bending around his or her finger when held up to a bright light is the same as gravitational lensing. Hi, ArtCamp. Actually, no, it's not. Light bending around your finger is a phenomenon called diffraction, and it's a behavior that waves do. All waves bend around corners. The gravitational effect predicted by Einstein is a different thing entirely. And finally, Michael Kingsford Gray claims that dark matter is the modern form of luminiferous ether. Hi, Michael. There's part of me that agrees with you and part that doesn't. It's certainly true that the term dark matter is a placeholder name for a solution to the mysteries I described in the last episode. We don't know the true nature of dark matter, or even if it exists at all. However, there never was any evidence for the existence of the ether. It was simply a postulate because nobody could imagine that electromagnetic waves like light could travel without a medium. After all other forms of waves need a medium. When Zwicky invented the term dark matter back in the 1930s, it was just a placeholder. But dark matter is a more advanced concept these days. Many, and I mean many, postulated explanations have been falsified. Killing ideas is not the same as discovering ideas, even though they are both crucial steps in the scientific process. But an honest person must admit that we don't know the final solution of the mystery of dark matter. We need to be open to all possibilities that have not yet been ruled out by measurement. Okay, so that's all the time we have for questions today.